Good morning, everyone. We are the team, the Next Gen Pragyan, with team ID 84406, and a problem statement for SIH25163 is Self-Healing Computing Elements by PDIC Department, Bharat Electronics Limited, and it comes under the theme Smart Automation with PS category as software. So now let's understand this with a hook story. Imagine an important defense system far away from anyone who can fix it. Suddenly, a key part inside breaks. In the past, this would be a disaster. The mission would fail, leaving a dangerous blind spot. But what if the system could find the problem, isolate the broken part, and fix itself instantly, all before a person even noticed something was wrong? This isn't science fiction. This is the problem we are here to solve. So, our idea, the shield, is an intelligent dual-layer defense mechanism which is designed to make any computing system capable of protecting and automatically recovering itself from failures or attacks. So, how do we achieve this? The shield transforms a vulnerable system into self-sustaining vault-proof environment, and it works by first using a real-time intelligence to continuously monitor all components and spot irregularities before they escalate. Second, it performs instant fault isolation, quarantining a malfunctioning block to stop a single fault from cascading. And finally, it autonomously recovers by dynamically rerouting tasks to healthy blocks, effectively healing itself without ever halting operations. Our proposed solution transforms traditional hardware into a self-repairing system which drastically reduces downtime costs and the need for human intervention. The hardware layer uses a self-reconfigurable FPGA that automatically detects, isolates, and repairs faults. The software layer is a real-time dashboard for visualizing the system's health and the entire healing process. To make it truly intelligent, we integrate AI to predict potential failures and use cryptographic verification. Our uniqueness and innovations are it uses AI powered predictive preemption that prevents critical failures by stopping them before they happen. The digital twin as a failure sandbox that safely tests and perfects the healing logic without risking physical hardware. A bio inspired regeneration BIR that enables flexible on site repairs for remote systems like satellites or autonomous vehicles. The resilient index, the hyper secure healing protocol. So now let's understand the technical approach. The technologies that we have used are for frontend, we have used HTML5, Tailwind CSS, JavaScript, and Chart.js for real-time dashboards. For backend, we have used Go or Python with Prometheus for live monitoring and analytics. For hardware, we have used Xilinx or Intel FPGAs for self-healing reconfigurable logic. In programming, we have used Verilog or VHDL for fault detection and dynamic routing. The process for implementation is as follows. First, we begin with the requirement analysis, studying FPGA fault patterns and defining our goals. Step 2, we design the dual layer system architecture including the self-healing FPGA fabric and monitoring dashboard. Step 3, in the development phase, we implement the Verilog or VHDL modules and the backend monitoring systems. In the step 4, we then move to testing where we stimulate the hardware faults to validate the auto-healing logic on an FPGA prototype. Finally, we scale the architecture for defense-grade system, integrating advanced features like predictive healing. The flowchart here shows the healing process in action. Dedicated watchdog modules constantly scan the active logic blocks. The moment a fault is detected, the system isolates it and instantly reroutes all input-output signals to a healthy spare block. Now let's understand the feasibility and the viability. First is the technical feasibility, which is high here, and it uses existing FPGA technology and has a working demo that proves it can find and fix faults automatically. Next is the operational feasibility, which is critical here, and it guarantees zero downtime by keeping systems running through hardware failures or attacks. Next is the financial feasibility, and it is high here. It saves money by cutting the need for manual repairs and uses standard hardware with little extra investment. Last is the scalability feasibility, which is modular here, and it is easy to expand by simply adding more spare blocks without needing to redesign the core system. Now, let's come to the potential risks and challenges and the strategies to overcome these challenges. First is the reconfiguration time latency, and the solution it preload the fix into fast on-chip memory to make repairs instant. The spare block pool exhaustion, and it uses a priority list to ensure the most critical systems always gets repaired first. Next is the corruption of reconfiguration data, and it checks the fix file's digital signature to verify it's not damaged or hacked before loading it. So now let's understand the impacts and the benefits. First are the benefits. First, it ensures the system continues to operate without interruption even if part fails. Next, it automatically fixes itself on site without needing a technician. Third, it protects against advanced threats and failures. Fourth, it eliminates the financial losses associated with the system shutdowns for repairs. Fifth, if a full repair isn't possible, it intelligently shuts down non-essential parts instead of crashing completely. Sixth, it applies hardware patches immediately as needed. Seventh, it increases the operational life of the hardware by repairing the wear and tear. Now we will understand the potential impact. The overall impact of the shield is to enable ultra-reliable, trusted autonomous systems across defense and critical industries by ensuring mission continuity and eliminating cost downtime. Given below are the list of research and references that we have used to build a prototype, the shield. In conclusion, The shield isn't just about managing failure, it's about making it irrelevant. We deliver on-site autonomous repair and ensure absolute mission continuity. This technology isn't just an improvement, it is the new standard for creating trusted self-healing system that can endure any challenges. Thank you.
We, the team NextGen Pragyan, has developed the working prototype for our problem statement self-healing computing elements. This covers the command center of main control and the status panel along with the strategic controls, and then it covers the resilient hardware fabric, the central grid, the brains of the operations, digital twin, charts and live services, along with the AI system analyst chatbot, the immersive experience and the system memory, and lastly a comprehensive logging and system memory. In this working prototype, we have covered all the system logs, attack histories that occur within the system, occurring and then activating the shield to reduce and resolve all the attacks for the better performance of the system. It covers all the strategic controls and the system logs with filtering so that the user can easily filter out the issues. It covers all the live service status that are visible. We can check the threat status, critical, coming or general. And this is the hardware fabric that show the faults in the hardware, and these are the charts, system logs and this is our AI system analyst.